Good afternoon, all those online. Just checking that you're seeing the screen and that you're also hearing me.
Good afternoon, sir. Yes, you are.
All right. First, apologies, but I had to get my daily exercise in because of the graduation ceremonies. So I parked on the hospital side and wound my way down here. And I guess I burned a few calories. So there is some good to the hustle and the displacement. All right, so today we are going to start a topic that we'll be covering over this week as well as next week. And it's about standardization. Now, you've learned a number of techniques to control for confounding. And you've noted along the way that it's important to get rid of confounding so that you can actually reach what we hope are definitive or valid conclusions. Standardization is one such way. It allows and facilitates for valid comparison. So let's see, here goes. And let me see if should I enlarge it a little bit? At home, are you seeing the screen or does it need to be enlarged a little bit? All right, let me try. So, one of the things we often do in epidemiology and in general investigations is that we compare disease rates. Now, if you're doing valid comparison, then you must ensure that you're essentially comparing like with like. That's something they teach you from primary school. You must compare apples and oranges, right? You must compare like with like. So questions that we find when we talk about comparing disease rates in epidemiology is, are we seeing an increasing incidence of disease? In order to answer that question, you have to look at disease rates now and disease rates before. Does it occur with undue frequency in my local community? In other words, does your community have an unusually high or unusually low rate of disease? And the only way to answer that is to compare your community rate with some other rate. So comparison. And then we will try to look at, does it correlate with some suspected cause? You have actually been doing this. You've been comparing incidents in the exposed to incidents in the unexposed. You compare rates. Has the outcome changed since control measures were introduced? So you'll have, for example, the death rate before COVID vaccination was available, and then we look at the death rate after COVID vaccination was available, comparing rates. Now, you can compare rates in a valid way if you have an ideal laboratory experiment. In such experiments, the investigator has total control over the environment and can vary only one variable at a time, one factor at a time. So you remember when you were in high school and they wanted to see what light does to plants, you get two containers, two plants, they put them in the same temperature, same room, except one is exposed to light and the other is not. And then you look for the effect. Now, it would be wonderful if we could isolate things like that in our world, but we often can't. So we always have to grapple with, is there something else operating? That factor is called a confounding factor. Something else, a competing explanatory variable, something else that might explain the cause and the effect that you're seeing. As this paragraph says, most epidemiological studies are observational. Your case control, your cohort, your quasi-experimental, but not truly experimental. Perhaps the closest thing to a true experiment is what? Your randomized clinical trial. That's the closest thing to a true experiment. Now, if such factors and differences determine risk of disease occurrently, then they are said to confound associations. Interestingly, several studies have shown high rates of lung cancer in cooks. Is this a consequence of their work caused by the fumes that they inhale from frying? We know that if you use refried and refried oil, over time, the oil breaks down and produces certain carcinogens. Thank God for Kentucky Fried Chicken. You take in a certain amount of carcinogens every time you eat. That's good. It builds up the resistance, That's good. So, is it because of the fumes why they have high rates of lung cancer? They're inhaling these carcinogens. Or is it simply that professional cooks smoke on average more than the general public? Now, any of you who have had the fortune of observing what happens at the back of many restaurants, you often see the cooks taking so-called breaks. And often they go around there and they have a good smoke break. So is it because they always are smoking during the breaks and therefore are exposed to higher levels of carcinogen why they have lung cancer? So smoking might actually confound the association between oil frying or inhaling fumes from oil and lung cancer. Or it could be the other way, that the association between smoking and lung cancer might be confounded and obscured by the fact that there are also these fumes that are causing cancer. It's important to establish confounding and control for it if you are going to make the conclusion that certain things are causal. Two very important confounding factors, and we're going to start with probably one example from this, are age and sex. We know, for example, that age is related to certain disease outcomes. So regardless of whatever else you are exposed to, age by itself may be increasing your risk for particular disease outcomes. Sex can affect the rates of disease in persons who have similar exposures, but yet males seem to occur more than females, or females seem to have worse outcomes than males. So we have to look at things like age and sex because they are commonly noted as potential confounders. Now, if you think about it, on your questionnaires, almost any questionnaire that's worth its salt, they always ask you age and sex. Because at some point, these factors are probably going to play in the outcomes that you're looking at. Now look at this table here. It's a table showing two communities in the United Kingdom, Bournemouth and Southampton. And we see here its annual death rate per 100,000, or you can convert it to per thousand if you prefer, for Southampton and for Bournemouth. Now look at the death rates. Bournemouth overall, the grand death rate is pen. No, that's not what I want. Where is this now? And all right, let's go back again and open it. I don't want this. All right, let's see. Why is this perpetually emerging? I don't want this. Let me see. Hopefully the pen. Bournemouth has pen. Let's go up to pens here and do a pen and color red. And hopefully the pen will activate. Still on yellow. Yes, now it's on red. And we'll get the thickness to about that. All right. So here is the overall death rate for Bournemouth. 1,694 per 100,000. Or if it's easier for you, 1.694 per 1,000. Right? If you want to convert it to 1,000, divide by 3, right? A factor of 10 to the 3. So this is 1.694 per 1,000. And for Southampton, the rate is 1.1190 per 100,000, or roughly 1.19 per 1,000. If that's easier for you, 1.694 per 1,000. Now, how did they get this overall debt rate? How do you generally calculate a debt rate? Anybody? Number of debts over the population will give us the debt rate. So let's do this. 5.5648 divided by 6674. 5648 divided by 6674. And what do you get? Anybody online, what did you get?
Sorry, Dr. James, can you repeat the figures?
Can you come? Here it is.
Yes.
5648 divided 6674.
0.08.
0.046. Sorry, 0.8. No,
0.846.
Yes.
So notice you
47.
didn't get
46.
or 47. That's fine. You notice you didn't get what's there.
No,
Anybody
sir.
has any idea why, when we just divided it so, we didn't get it? Notice at the top, it says debts over a 5-year period.
5-year period.
And notice here, it says the annual debt rate. So it's a yearly debt rate. So what we have to do is divide further by 5.
By
And
5.
let's see what you get.
0.017.
Because this is the number of debts. The total,
0.0169.
0.01694.
Yes, sir.
Yes, sir.
So of course, there should be some other zeros in front of that. So if you want to convert this to 100,000, we have to move the decimal place, what, 5 points? 1, 2, 3, 4, 5, which would give us 1,694 per 100,000. Or if you want to convert it to 1,000, we move the decimal place 3 points. And we would have ended up at 1 There should be another 0 here, right?
Where? No, there's
Yes.
not a 0.
1.69 per thousand. Because
So
that's
the
5
number,
decimal place.
the original number is 0.0169.
0.0169.
1694. That's the original figure.
4. Right. So that becomes 5 decimal places is 1, 2, 3, 4, 5. Correct? Yeah.
1, 2, 3, 4, 5.
Right. So it will be 1.694 per thousand. And if you per 100,000, and if you want to
Yes.
divide that further, we'll get divide by 1,000. This will give you 1.69 per thousand. Correct.
Okay.
Now, so that's how it goes. So what they've done for each of these lines is to divide the number of deaths by the population and then annualize the death rate. So this will give you the death rate over the 5-year period. And then you could annualize it. You could have gotten the same figure by dividing this figure by 5, saying if there are 5,000 deaths, you're roughly around 1,000 deaths per year. And then divide it and you'll get the same answer. So if we take it for what it is, and that they've done all their calculations correctly, we could actually do the same for the age groups. But before we do the same for the age groups, if somebody showed you these death rates, where would you choose to live? Bournemouth or Southampton? Well, most people will say, I want to live where the death rate is lower.
Lower.
So
Southampton.
Southampton seems to be carrying the swing.
Mm-hmm.
It looks like Bournemouth is a less healthy place to go than Southampton. Or we might say Southampton is seemingly the more salubrious place to go.
You cannot draw that conclusion.
Notice the word seemingly, right?
Yes, sir.
All other things being equal. But are all other things equal? That's a good question. Now, let us look at the death rates by age group. We see the death rate by age group. Bournemouth is much higher than Southampton, or certainly a little higher. For the age under 1, the infants.
Mm-hmm.
For the age 1 to 44, Bournemouth is still slightly higher. So Southampton seems to be still carrying the swing, even though the gap is not so big. But for 45 to 64, who has the higher death rate?
Southampton.
Southampton has gone with the higher death rate. And then let's look at the 65 pluses. In terms of the age-specific death rate, Southampton has gone with the cake. So, why is that? Why is the, somebody says NCD look like it lick in Southampton. And why would NCDs hit Southampton?
Because it has an aging population.
Because they probably have a far more aging population. The age distributions might be very much different. And so if you have, when you look at details, if you have an aging population, within those age groups, the population that has a greater proportion of aged people are going to have higher death rates because a higher age is a risk factor for death. So if you have lots more old people, you are actually going to end up having lots more deaths among the elderly.
Bournemouth have more.
But doctor,
Yes.
good afternoon. I am seeing where Bournemouth has
Yes.
mic is
Go
off,
ahead.
Simone.
You're onto something.
Simone, your
Go
mic
ahead.
is
You're
off.
onto something.
so thanks, Sean. So in Bournemouth, they have a higher population in the 65 plus. So
All
what is
right.
happening?
Good. So let's look at proportions. She says, let's look at the age distribution by proportions for Bournemouth and Southampton. So let's look at 65 plus. Anybody, can you take a calculator? 11,760 divide 66. So that's 11,000 divided 66,000. This is about 1/6. So that should be close to 12%. What did you get?
0.176.
17%. All right, so roughly 17%. 19 out of 66. So almost 20 out of, that's close to a third. Slightly, about 30%. Somebody tell me.
29.
29%. 1 to 44, 34.
616.
Out of 66, almost 50%.
52. 52.
52%. And the population in the infant group, roughly 1,000 out of 66,000. About 2%.
Yes.
Little bit.
1.3 actually.
1.3%. All right, great. Let's do the situation for
The other side.
Southampton. 9120, the 65 plus is out of 99. That's about what? 1/10, 1/11, 10%, 9%,
9.1, 9.2.
9.2%. Next one, 24 out of 99. That's 25 out of 100. That's like 25%.
25%. Yes, sir.
64 out of 99. That's about 2/3. About 66%, 60.
64.
64%. And 1897, 2,000 out of roughly 100,000. That should be about 2%.
1.9.
1.9%. So, very interesting that Bournemouth has a higher death rate overall. And that is not surprising because when we look at the age distribution, which population has the greatest proportion of aged persons? Is it Bournemouth or Southampton? When you take, for example, the 45 and upwards, 29% and 17%. Compared to 25 and 9. So these have about 34% of their population above 45. This one has 47% of their population above 45. So naturally, simply because you have a higher proportion of persons in your population that are elderly, you are going to have a higher death rate. Regardless of how healthy or unhealthy the place is. So what might be driving Bournemouth's rate is the fact that they have such a vastly higher proportion of older persons. But of course, when you do the age stratification, that sounds like a good word to control for confounding, and you look at the strata, you find that Bournemouth is not predominantly overwhelming the worst place. In sometimes they have a higher death rate, sometimes the death rate looks almost similar, and sometimes lower. So apparently, age is confounding the relationship between place and death rate. The age distribution will affect overall death rates. And it turns out that Bournemouth is a place to which many English persons retire. So it's not surprising that they have a higher proportion of older persons. And consequently, they have a higher death rate. So it's not necessarily that Bournemouth is a less healthy place in terms of the environment and pollution and health risk and so on. It's just simply, maybe both places are equal, but simply age alone is driving the differences. Or maybe, in fact, Bournemouth is worse, but you cannot say, as someone said online, make that conclusion until you have control for possible confounders. Are we comparing like with like? Certainly, when it comes to age, we are not comparing like with like. All right, just an observation. So, we want to explore this idea a bit more to show how comparison of crude rates could be affected by different underlying distributions of a given factor. Factors such as age, sex, race, income levels. And to understand that, we are going to show you that a crude rate is actually a weighted average of individual category-specific rates, with the weights being the proportion in each category of the population. So overall, and now don't get bogged down too much with what I'm going to do, is I'm going to show you that the crude rate is the sum of the age category specific rates multiplied by the proportion in that category, the proportion of the population in that category. We're going to use age. Look at age distribution, the proportions of persons in each age category, and the age category specific rate. Here's some data concerning mortality rates from cancer in the USA 1980. We have the age distribution, the number of cancer deaths, the population at risk, the mid-year population, and therefore we can calculate the mortality rate, the death rate. For example, in the under 5 group, there were 686 cancer deaths over the population of 16,348,000. And just for calculation of one, we're just going to do 2 of them, just to check that these tables are correct. Somebody can do a death rate is number of deaths over mid-year population, the incidence of death. Here, the population at risk for death, typical population. So in this case, the first one, we get 686 over 16,348,000. What do we have? What did you get? Read me the figure.
4.196.
All right. Give me the raw figures first.
0.000
491
42
49
42
42
0 again
0
8. You want all
and the
of it?
last digit. Yeah, just give me one more digit.
8 8 8.
888. All right. All kinds of things. So notice this is what we have. We could either express this as rate per 1,000, or they have chosen the table to make it rate per 100,000. So for 100,000, we have to move the decimal place 5 places. All right.
Doctor?
There's 1 0 missing.
There's a 0 missing. Yes, definitely. Yeah.
Yeah, does that mean yes, there's 0
Correct.
missing? Just
So if we move it 5, it's 1, 2, 3, 4, 5, which is 4.2 per 10 to the 5th, or 4.2 per 100,000, which is what they have. Makes sense? So they are good students who compile this table, and we don't need to check their rates, right? So we assume that all the rates are correct, and that is it. They have also calculated the total or crude death rate. And remembering from the first term, the crude death rate is number of deaths over total population, right?
yes, sir.
The overall grand death rate, the crude death rate. So if we look at the total number of deaths, in terms of the cancer deaths, it will be 416,481 divided by the total population. And if you add up all of these populations here, you will get 226,546. 000. And anybody who does that should get 0.00018, 4 zeros and a 183, or
No, I got 0.00183.
0.00183, correct?
Right.
8 or something like that, or 7 something,
8 again.
and therefore it's 183 per 100,000. So if you move the decimal place 1, 2, 3, 4, 5, 3 and 2, 5, I have one extra 0 then, because it's supposed to land here. 0.0018. There's an extra 0.
It's 2 zeros, sir. 0.00.
Right? So it's 1, 2, 3, 4, 5 to give you 183 per 1,000, per 100,000. All right. So the overall crude death rate is 183 per 100,000. That is a given. That is no extraordinary brain power required. We know a death rate is simply total number of deaths over total population. So that is the death rate. Now, we could also look at this in a different way. How was this total derived? We can do this in another way. We can say this total was derived by getting 686 plus 777 plus 720 plus 1145 and so on. That's how we got the 460, the numerator. Now, simply by playing with this formula, you can see 686, which we derived here. If we say number of deaths over that equal death rate, then equal is, we can say number of deaths is also equal to the death rate multiplied by the mid-year pop. Just cross-multiplying this. Just playing with the formula. So the number of deaths can also be seen as death rate times the mid-year population. So instead of writing 686, I can write death rate 4.2 multiplied by 16,348. That's the same as 686. So all I've done is to rewrite the 686 as equal to 4.2 multiplied by 16,348 million. All I've done is change this formula, bring this up here when you cross multiply, so that mid-year comes there. All right. So what I'm going to do is every time I have 686, I'm going to put 4.2 times 16,348, 000. Where I have 777, I'm going to put 4.7 times 16,700, 000. Where I have 720, I'm going to put 18. I'm going to put 3.9 multiplied by 18,242, 000. Where I have 1145, I'm going to put 5.4 multiplied by 21,168, 000. And so that's what I've done here. The 686 is 4.2 times 16,348. The 777 is 4.7 times 16,700, 000. The 720 is the same as 3.9 times 18,242. And the 1145 is the same as 5.4 times 21,168. And I have gone through the table right down to that last figure, which says this 130,000 is the same as 1.37, 1.313.7, not 1313.7 multiplied by 9969,000. So everybody is comfortable with the fact that I'm just replacing the deaths by a little formula to get the same figure. Now, if you do that and you were to take your calculator and do 4.2 times 16 times that, you're going to end up and divide at the end by 226,546. You're going to end up with 183.8. So it shows you to a certain point that if you sum up the age-specific category rates multiplied by the population, you will end up with the number of deaths overall. You sum them, and then you divide, you can get the rate. Now, here's a little trick further. And to demonstrate this trick, I'm just going to go back to primary school maths. Suppose you have a number, 3 plus another number, 4 let's choose a number that is easy to divide with, plus 3 and 4, 7 and 2, 9, 7 and all right, let me do let me do 6 plus 4 plus 2 over 12. Make it simple. Suppose you are given, this is a grade 3 maths problem. 6 plus 4 plus 2 over 12. What would your answer be? 1, right? Correct.
Yes, sir.
Because that's 12 over 12 equal 1. Now, is this the same as 6 over 12? I could break down the fraction plus 4 over 12 plus 2 over 12. So anybody does that and tell me what you get. 6 over 12 plus 4 divided 12 plus 2 over 12. And please put them in bracket because division always comes. You should get back 1. Great. This is great. Great to do that. Lowest common multiple added fractions. So what I'm going to do is I'm going to do the same thing. If I have a number over plus another number, plus another number, plus another number, over a common denominator, I can break it down by dividing each number by that given denominator and adding it up. It will give me the same answer. So all I've done here is 4.2 times 16,348 divided 226,546. This would be like the 6 out of 12. Then the next number divided by that, then the next number divided by that, then the next number divided by that. And if you do it, you will get 183.8 per 100,000. All right. Now, very interesting. Having said, yes, this is the math. If you look at the form I've given you, say, for example, this first one. This first one could be written as 4.2 multiplied by 16,348 000 divided by 226,546 000. When we look at the quantities, what is this? This is the age-specific rate. So if you go over that, the 4.2 is the age-specific rate, the death rate in that age group. And then look at the other factor, 16,348 000 divided 226,546. That is really the proportion of the population that age group constitutes. So out of the grand population of 226 million, we have 16,340, 226,546 000. We have 16 million of them out of that 226 million being under age 1. So this is really the proportion in each population. So really and truly, if you want to calculate the death rate, another way of calculating it is to say, take each category's specific rate, multiply it by the proportion in that category, which would be this multiplied by this, and then add them up, which is what you've done here. All of that calculation I'm going through is just to illustrate one thing. Nobody's going to ask you to do that. But just remember that a crude death rate is the sum of the age-specific category rates times the proportion in that population. So each proportion is going to contribute a certain amount to the death rate. Larger proportions will constitute, depending on the death rate, a greater amount. All right, so we just hold this. We shall utilize this knowledge at a later time. So that's the only message to take home from this page, that accrued death rate is equal to the sum of the age-specific category rates times the proportion in that category. Now, showing you something even more interesting. Even if two populations have the identical age-specific death rates, age category death rates, the population proportions can cause different death rates. So even if the death rates are the same across all the categories, it all depends on the proportion in each category. That's what determines the death rate. Take two populations here. Population X and population Y. Notice here that the death rates are all the same. In population A, the under 5 death rate is 4.2 per 100,000. In population Y, or X rather, it's also 4.2. The death rates are exactly the same. So your intuition would say to you, but if the death rates are the same, then the overall death rates in each category, the overall death rates ought to be the same. That's the thinking you might have. Because people are dying at the same rate in all the age groups. But look at a little mental game I've played. I have made the population in each age group extremely similar. Similar in all respects, except at this point, these 2 points. In population X, I still have made it such that they have the same amount of people, 226 million. But I've changed the number of people in the age 20 to 24 age group from 21,319 to 99,69,000. So all I did was remove this 99,6,000, which was down in the 75, and put it here, a mental game. And I take the 21,000 and put it down here. So the death rates are still identical, but the population distribution has changed. Because originally, if you notice, in population X, the proportion in the 20 to 24 age group was 21 million out of 226 million. That's about a 10th. About a 10%, 9%, 10%. Somewhere around that. Anybody who wants to do it can do it. Whereas in the 75 age group, this was for population X, it would have been 9.969 out of 226. Somebody just quickly get me the proportions. 21,319 divide 226,546. So it's 9.4%, roughly. And 9969 divide 226,546. That's about a tenth, or not a tenth. 4.4%. All right. Now, the same thing is going to happen over here if you do, because the total is the same. But this time, the 4.4% is here, and the 9.4% is here. So in population X, the age group 2020 to 24 constitutes 9.4% of the population, and the age group 75 plus constitutes 4.4% of the population. While in population Y, the age group 20 to 24 rather constitutes 4.4%, and the age group 75 plus constitutes 9.4%. Remember, the death rates are identical. Now, if we do the calculations and calculate the crude death rate for population X by doing that same thing that we did before, you'll get 183 per 100,000. That's the same data from the first table. If you then go to population Y and you do it, 4.2 times 16 that, 4.7 times that, 3.9 times 1842, 5.4 times 21,168, but the next one will be 7.2 times 99,69,000. If you go through and you do that, you'll get the death rate being 249.2. Population Y will have a much higher death rate than population X. They have identical age-specific rates. The only difference is the proportion distribution by categories. And you will notice that in this population, when population Y, when you had a much larger proportion of persons in the older age groups that had the higher death rates, 1,000, naturally, the death rates ballooned. So the take-home message here is that, let's click on this and find it. Where are you, Mr. Mouse? The take-home message is that different distributions of underlying characteristics between populations or groups being compared may cause differences to be observed in the crude mortality or crude whatever rates you're calculating. Therefore, these underlying distributions potentially can explain the differences in death rate. And something that can explain it other than certain given factors will be a confounding factor, a competing explanation for the observed difference. Therefore, differences in age distributions in populations can cause different death rates. Differences in sex distributions difference in income distributions, difference in occupational distributions, differences in race distributions, differences in religious distributions. All of these can cause differences in the rates you're interested in. And therefore, if you are looking at another factor and observing differences, you must be sure that the differences are not due to these other things called confounding, such as age, such as sex, such as race. Classic ones, and I'll give you, there's an example in a practice exercise to come. Differences in murder rates. Is it that populations are just wickeder, so to speak, more wicked than others? Or is it that the differences in murder rates are not due to the wickedness of people's hearts, but due to simply unemployment, differences in unemployment rates, differences in welfare systems, differences in age groups? Because who are the people committing most of the murders? They are young people. And therefore, if you have an older population versus a younger population, by the very fact that they are younger, not to mention their wickedness, the very fact they are younger is likely to cause a higher murder rate in a particular population. Young people get into fights and violence and this. Old people, they can't even move. Or, you know what, they say, me can't bother. Differences can cause this. Therefore, to facilitate valid comparison, we need to control for confounding. Look how long I've spent trying to do this. See? I could have said that. But I wanted to show you because we are going to use a method that looks at these kinds of comparisons by underlying distribution. We need to adjust for confounding. Many methods exist for controlling for confounding, including, just as a quick refresher, here are the ones that you know of. What are the methods you have met, which is said to...
matching stratification.
All right, let's you're on the money as usual. Matching, right? Somebody said stratification. Somebody said regression.
I think multivariate analysis, standardization.
Multivariate analysis is tied up with regression, right? Same thing, multivariate analysis.
I think randomization as well.
Randomization. That's correct.
Standardization is another method too.
All right, standardization. She says, yes, we can standardize, which is the one that we are going to learn. And there's one other that you've met. What's called? Exclusion. Exclusion, otherwise called what? Restriction. So if sex is a confounder, you just say, let's look at females only, and then let's look at males only. So these are 6 common methods for controlling for confounding. Sometimes people say, these you do in the design phase. So when you're doing the design of your study, you match and you randomize and you restrict. While these are done in the analysis phase of your study. So after you do your study now and you get your results, you can say, I'm going to control by stratifying, by performing a stratified analysis, doing multivariate regression and all such the like, or doing standardization after you've got your results. So you can control for confounding by methods in the design of your study, the design phase, and by methods in the analysis phase of your study. So, we saw in Southampton, Bournemouth example that we ought not to jump to conclusions based on comparisons of crude rates. We saw that we could go and look at the age categories and see what was happening. And what we saw was that Bournemouth was higher sometimes and Southampton higher sometimes. And it wasn't just things are just higher in Bournemouth. But it's tedious to go through such tables. Very tedious. So what we try to do is to come up with one single measure that will correct for and control for confounding. And this is done through standardization by the generation of standardized rates or adjusted rates, as they are sometimes called. So when we adjust because of age differences, we can say we age standardize, or we can say we have age adjusted. We have taken the age factor as a potential confounder into account, and we've adjusted it, and we've come up with a new figure so that you can do the valid comparison. There are two methods for doing it. The first is the direct method, and the second is the indirect method. And we shall now see how these methods are done. And we shall do some examples to concretize it. Now, let me see if I can find. There's a handout called Steps in Age Adjustment. Let me see if I find the folder. Steps in Age Adjustment. The procedures. Now, I'm going to walk you just at first through the procedures. And then I'm going to go step by step and explain what we are doing. And then you'll say, oh my God, it's that simple. So, steps in adjustment or standardization. We have to choose a population to serve as what we call the standard population. Remember, we are comparing populations, comparing groups. So one of them has to serve as the standard, or you can get a standard from outside. Then you have to decide which method are you going to use? The direct method of standardization or the indirect method? If you decide to do the direct method, then you follow the instructions on the A. And if you decide to do the indirect method, you follow the instructions on the B. One of the two big questions are supposed to be in your mind. First, how do I choose a standard population? And the second, how will I know which method to use? These are questions we are going to answer. But I want you to be able to master both techniques first. It's like me saying to you, there are at least two ways to kill a dog. You could hang it, or you could shoot it.
DJ Simone, can you mute your mic, please?
You could hang it, or you could shoot it. You're going to ask me, how will I know which one to do? Well, what I'm going to do is I'm going to train you on both methods, and then allow you to use judgment based on certain guidelines to say, this dog, I'm going to shoot it, you know. You know why I'm going to shoot it? It's a wild dog running all over the place. And therefore, I'm going to use the shooting method. Whereas the other dog is another docile dog. You just say, I'm just going to walk up against him and throw a rope on your neck and hang him. So we will see the circumstances eventually as to which method to use, but I'm going to train you on the methods first. It's kind of the kind of thing they do in karate. They tell you, they teach you 2 or 3 or 4 techniques to slay your assailant. Whether you want to flip him on this, or you want to do the thing, or you want to give a blow to the groin, or elbow to the face. And you know that if they come from behind, you must elbow back to the face. And you know that if they confront you, a good kick to the groin, especially a male, is a very devastating thing. So you know the circumstances on which to use which technique. So the direct method, let's talk about it. In the direct method, once we have chosen a standard population, it provides the category distribution or the population numbers. So the standard population provides the profile of the factor you're interested in. So if you are looking at the age, if you are looking at age and you are thinking age is a confounder, the standard population provides the age distribution, the age composition, the age profile. The other population, sometimes they give the other population name like index population, study population, other population. The other one you're comparing. And so other is sometimes referred to other, aka also known as index, also known as study population, index population. And please don't confuse it with the study population that you know in research methods. Sometimes called index, sometimes called study, sometimes called the other one, apart from the standard. So the procedure, you're going to multiply the numbers in each age category in the standard by the rates from the other population. This will yield the number of expected cases or events. We total the expected cases and divide the expected cases by the total standard population. And that will directly give you the age standardized rate of the other population. And then, of course, we compare the adjusted rate to the reference group or the standard population, and then make conclusions. Now, these are the steps. They are mechanical. But now that I'm going to go to the demonstration, you'll understand what these steps are actually doing. Here is a table showing age adjustment. We are going to do it on the basis of adjust because of age differences. We could have said race adjustment, income adjustment. And we are going to use the direct method. So notice it says using the direct method. Here's some data from a population, population A. It shows you the age distribution in population A. 15,000 in the under ones, 64,000 in the 1 to 4s, 169 in the 5 to 17s, the greater than 65, 96,000, and a total population of 724,467. It also provides the deaths occurring in that population by age group. 370 people died in the under ones, 45 in the 1 to 4s, 68 in the 5 to 7s, and so on, yielding a total of 10,370 deaths. Data is also provided for another population, population B. They have 28,000 in the under ones, 98,000 in the 1 to 4s, 517,000 in the 310s, and so on, yielding a total population of 776,806. They also have data about the deaths. 898 in the under ones, 157 in the 1 to 4s, 187 in the 5 to 17s. And by the time you get to the 865s, we have 3,101 deaths. If we take the crude death rate in population A, we can obtain it. And we can also do likewise in population B, obtain the crude death rate. How do we get a crude death rate? Number of deaths over the population. So in population A, the death rate is going to be 10,370 divided by 724,467. And when you get that, you should get 0.00, that's what, 143? 143. There's an extra 0 there. 0.0143. And if you convert that to per thousand, sorry, oops. Yes. 1, 2, 3. You'll get 14.3 deaths per thousand. Notice the per thousand, important. Mortality rates per thousand. Unadjusted death rates per thousand. And we can do likewise for B. And B will be calculated by 7,891 divided by 776,806. And if you get that, you should get 0.00102, which is 10.2 per thousand. Moving your decimal place 3 places.
Wait, is 0.0102?
0.0102.
2.
Correct. So when we do 1, 2, 3, 10.2 per thousand. Great. So if we look just at the figures as they are reported, we would be tempted to make the conclusion that death rates are certainly higher in population A than in B. Maybe it appears that population A maybe is in a terrible state, why they are dying at such a high rate compared to B. But remember we said something, that underlying distributions can affect overall death rates. Just as a quick check, what proportion of the population is age 1 to 4 in population A? Just as a quick check. It will be 64,978 divide 724,467.
Around 8%.
How much? 3%?
I got
Somebody online said something.
8.96%.
8.9% roughly, or roughly 9%.
9%, right.
So let's round up. About 9%. In what about population B, age 1 to 4?
That's 9.
What proportion of their population are, for example, in the 1 to 4 group? 98,000 out of 776.
776, 806. So that's 12.6, so roughly 12.6.
12.6%. Roughly. Let's look at the age 65. Let's see. 96,000 out of 724. There's 100, about 1/7. So that's about 17%. 13?
13.3.
13.3%. And the other population B in the 65 age group? %13.3%. Will be 40,000 out of 776.
It's 5.3.
5.3%. So already, without going through, we could have done it for all the categories and work it out, but we don't have to do it. Already we can see that the population distributions are different when it comes to age. And once population distributions of a factor is different, there is the potential for confounding. So in comparison, we must take that into account. And we're going to take that into account by standardization. So according to the method, it says we choose a standard population. I'm not going to tell you the criteria, choose a standard. But notice right now at the top, it says at the very top, what it says. Population A will serve as the standard. Now, according to the instruction sheet, it says we multiply the category rates from the other population by the population numbers in the standard. The population numbers are provided by the standard, and the rates come from the other population. Now that sounds complex. But guess what we are going to do? We are really saying what if B and A are different on the basis of population distribution. But what if B look just like A in population distribution? Then we would have eliminated the population distribution factor. And then we can compare like with like. So what we say is, what if B looked like A in distribution? Sometimes people want to compare runners. And they take a 6-year-old and look at the time they run for the 100 meters. And they take Usain Bolt and the time he runs for the 100 meters. And they are going to compare their two times. Everybody would say that's unfair. Agreed. But what we can do is we say, What if the 6-year-old had muscles like you see in Bolt, and had this like Bolt, and look like Bolt? I wonder what he would run. We often do the same thing for cars. We compare the Mercedes with the 2000 liter cc engine, and we put the Toyota Corolla with a 1500 cc engine, and we start to compare the cars. Well, that's not valid because the engines are very different. A fair comparison. But what we can do is to find out if the Toyota Corolla is made better than the Mercedes Benz, apart from the engine. We could say, suppose you put the Mercedes engine in the Toyota. I wonder what the Toyota would do. It doesn't automatically mean it's the perform like the Mercedes because there are other things in the Toyota. But at least we could be comparing fear and fear. It's just like what they do in athletics. Some people run a race and they run it at high altitude. And then they get some fast time. And then they come back down to the low line and say, then they can't run the same time. Because people say, what if you had run that race at low level? What time would you run? This will tell us whether you are good like the other man who is running at low level. So what we really do is we superimpose the population profile of A onto population B. We say, let population B look just like A in its profile. So what we are going to do is we are going to change here. We already have established that there are underlying differences. We're going to say, let it look like population B. 15, 461, 64, 978, 169, 344, 198, 574, 180, 105, 96, 005. And of course, the denominator for all this will be 724, 467. Because if you add those up, they come to that. So now, what we've done now is to say, take out the age factor thing. Go ahead, somebody online.
Yes, doctor, I had a question. How do you choose which population to use as a standard?
All right. Earlier, I said that would be a secret.
Sorry.
And I will tell you at the end. But that's all right. But I was saying, if you're listening, that I'm going to teach you how to kill a dog. I will show you the shooting method, and I will show you the hanging method. And then later, I'm going to give you some guidelines so that you can choose whether you wish to hang the dog or to shoot the dog, right?
Okay, no problem.
Not a problem. Not a problem with your question. Good question. So we say it now looks like A. No longer. It's now looking like A. So what deaths would we expect in population B if it looked like A in age composition? We know the death rate for the age group in B. They are there. 31.2, 1.6 per thousand, 0.6 per thousand, 0.48 per thousand, 0.2.6 per thousand, 75.9 per thousand. So in order to say how many deaths would occur in B if it looked like A, we just do the same thing. If you want number of deaths, you multiply the death rate by the population. So the number of deaths generated here equal 31.2 per thousand multiply by what number? What number should I multiply by? 15 461. Because it now looks like A. So we have made the two populations look alike in age profile so that we can see what's really happening in B and compare. Now, please don't forget the 30 this per thousand. People often forget them doing calculation. Mortality rates per thousand. So that will equal to 31.2 divided 1,000 times 15, 461, right? And you can calculate it and tell me what you get.
Yes, sir.
Did you get
482 roughly. It's 482.3.
482 rounded up?
It's 140. It's a 482
Yes.
rounded out.
Right. You're gonna get 482 point something. And for just for practical purposes, we're not going to have 0.5 of a death and 0.3 of a death. Although for theoretical purposes, it does exist. So you round up, so you'd have expected 482 deaths. What about the second one? Age group 1 to 4. What would you have expected in terms of number of deaths in B if it looked like A in the 1 to 4 age group and the death rates in B are applying? This is the kind of thing. What would it have looked like if Melissa had hit Haiti in the same way that it hit Jamaica? What if Jamaica, or better yet, what if Jamaica had the housing profile of Haiti? You can imagine what would happen. That's what we are doing. What if Jamaica looked like Haiti? What would have happened? Okay. And so for the second category, did you get 104?
Yes, sir, when you're round up.
When you round up, you get roughly 104.
0.9, so it's 104.
All right. Let's do, just for checking, 45 to 64. We're going to assume that the people who compile the table got the 5 to 17 right and the 18 to 44 right. Then we'll have a break in a couple of minutes. Let's do the 45 to 64. What deaths would you expect in B if it had the profile of A in the 45 to 64? It would be 22.6 per thousand multiplied by 180, 105.
Yes, sir. We got 4,070.4.
4,070.4. Each rounded up is 4,070.
Yes.
And for completion, let's see what deaths would be expected in the age 65 group if population B had the profile of A.
Yes, sir. 7,286.7. So 7,287.
All right. So remember, the number of deaths that are expected can be calculated by the death rate. Any death rate times the population will give you the number of deaths. So what we are doing is taking the population. We pretend that these don't exist. We have superimposed it onto B and say, let it look just like A. What would have happened? So, how many deaths overall would we have expected? What we do to get the total number of deaths expected is add up all the ones we've done. And you should get, if it looked like A, we would have gotten 12,998 deaths. So what we've been doing is linking this and this, linking this and this, linking this and this, linking this and this, linking this, linking this. We would have expected 12,998 deaths in this population. What is the size of this population? Now that we have superimposed the profile, it's 724,467, the same as the standard. And therefore, having adjusted for age, having controlled for age, having standardized the age profile, the death rate would now be 12,998 divided by 724,467. Total now, death rate is the total, the crew death rate, total death rate, deaths divided by the population. Notice we didn't use this population. We use this because it now looks like A. So it must total like A. And we get the death rate being 17.9 per thousand. So what this tells us is that B, if B was just like A in age profile, the death rate in B would be 17.9. In fact, B would have a higher death rate than A, the standard. If B looked like A in population, it would have a higher death rate. Another way of looking at this, it's only because of the age distribution difference why A is higher than B. But having adjusted, the truth reveals itself. Having adjusted, we can do valid comparison. We can compare population B truly with population A because it's like and like, and we're looking at death rates, mortality. This rate is called the age standardized rate, also called the age adjusted rate, because we adjusted the age profile. So use any term you like. the adjusted rate or the standardized rate. Both are acceptable. Now, the crude one, before adjustment, 14.3 and 10.2. Having adjusted, we still have the standard, 14.3, but now the other population would have had a death rate of 17.9. And so what this tells us is that the force of mortality, the Grim Reaper, is really more active in B than in A. It's just because A did have more weaklings, 13.3. You know, A did have some more old people than B. But all in all, everything else fair, B would have a higher death rate. Now, some people go a little further. They go and they say, having compared it, 17.9 to 14.3, notice, we will get 1.3. 17.9 divide 14.3 gives us 1.3, suggesting that the death rate is 1.3 times more in B than the standard. And notice the standard is in the denominator. Because this is what we are comparing things to. You have, let's say we say 50% is the standard pass mark, and you get 75. We can say you are 25% more than the pass mark. You are 1.25 times higher than the pass mark. So this is what you do. You can compare it further and say, it appears to be 1.3 times more. Now this could start to ring a little bell. Have you been doing some stuff where you're saying something is 1.3 times more at risk of happening than others? It's almost like a relative risk. That's right. It's one rate relative to another. All right? And in fact, we give it a special name. It's called the SMR. When you compare it, it's called the SMR, Standardized Mortality Ratio. Standardized. In this case, because we are comparing deaths, it's mortality ratio. If it was incidence of something else, we call it standardized incidence ratio. Or it's whatever it is, SMR. All right, we're gonna give you the CMR. That is the term that people are gravitating to, the SMR. But in the old books, you might not see SMR, you might see CMR. The comparative mortality ratio, CMR. It is the same thing. Some people say, when I did by the direct method, I call it the CMR. But when I do it by the indirect method, I call it the SMR. No matter what you do, it's still 1.3 times higher. Whether you call it SMR or CMR. Nowadays, people are saying it's the same thing, so let's call it SMR. But you still are going to see in some books the CMR or some papers. But it's still a standardized way of reporting how much more is the risk of dying in one population versus the other. Note here what we did, because we are just about to break. Noted what we did. We took the rates from the other, the standard provided the profile, and the rates came from the other. Now, I could have just done this, 31.2 times this. But I didn't want you to do that because I wanted to see you to see what we're doing is actually making it look like the other population. And then we can see what would happen. And then we can make the comparison. So that is the direct method. Now, if you go back to your notes, the second note, you'll realize that what we did here is what's described. Where is the mouse hiding? Lord. Where is it? All right, slow down. What we did is what they describe here. The standard provided the population numbers, the other one provided the rates. We multiplied the numbers in each category by the rates. And this yields the expected cases for each layer. We total the expected cases, the 12,999,998, and then we divided that by the total standard population. And then we got the age adjusted rates. It is called the direct method because when you did this, you obtained the rate right away. As soon as you finish the 12,998 over 467, you got the adjusted rate. When we come back after the break, you'll see we have to do, in the other method, you have to do a step further and then you get the rate. So you get it indirectly. That's why it's called, one method is called the direct method and the other called the indirect. In the direct method, you get the adjusted rate right away, directly, and then you calculate the SMR. We shall see the other method, you end up with the SMR, and then you have to calculate the rate in that further step. All right, let's take a break. It's what, 10 to 7? What time do people want to come back? 7:15? You tell me, or if you want to come back earlier, it's fine with me. Online, how many minutes you need?
7:50. What?
So
What?
we 7:15, we resume at 7:50. All right, 7:15, we resume. In the meantime, while others are going on the break, are there any questions so far? Anybody here? Somebody answered, but your mic was on. It's muffled. Let me see, who is it? That's muffled. All right, we are back. And we still have everybody with us, which is good. So before the break, we looked at the direct method. And just as a reminder, the steps are essentially, you're going to make the population's comparison. So whatever is the standard provides the profile. And then you ask, what would happen in the other population if it had the profile of B? And so we apply the rates, we get the expected deaths, we total them, and then we generate an overall death rate. And that gives us the age-adjusted rate. We can then go a step further if we wish. We got the rate already directly, but sometimes you may want to go a bit further by comparing the new adjusted rate to the standard. And therefore you can see how many times higher is the new rate than the standard. So you can say after adjusting, the rate is 1.3 times higher than in the standard, 30% higher. All right, that was in the direct method. Now let's just look at the steps for the indirect, and then we will go and see how it's actually done. In the indirect method, the standard population provides the rates. Notice, in the direct method, the standard population would provide the category distribution, the age profile or whatever profile you're looking at. In the indirect, the standard does not provide the profile, but instead provides the rates. The other population then has the population numbers. So in other words, in the indirect method, we are really saying, what if, for example, if A is the standard, what if B had rates like A? Previously, we said, what if B had the profile, population profile of A? Now we're going to say, what if B had the rates like A? And then we do the same thing. We use the rates, multiply by the population, and then generate the expected deaths. This is where now the indirect method has a second difference. Once we get the expected deaths, we compare it to the deaths that were actually observed. So the expected or calculated deaths, all right, are called the expected. And we look at what actually happened compared to what we expected. Observed to expected, O to E. And that will give us a ratio called the SMR. And then we go one step further because it generates the SMR, but it doesn't give us the adjusted rates. We can then interpret the SMR and calculate the adjusted rate. So we shall do that. And then you'll say, oh my God, this is easy. So let's go to our table now. Down more times. Same data. Notice it already says at the top, population A is the standard. I'm not telling you why, right? No, I'm just teaching you the technique. Decide on a standard population. It is A. That's just a pill to swallow right now. And then choose the method, A method. This time we are going to use the indirect method. And then we are going to follow the procedure. In the indirect method, the standard population provides the rates. So here are the rates. A is the standard, so these are the rates we are going to use. And the other population provides the numbers. So we are really saying, what would happen if B had rates like A? Because we always say like the standard. The standard, always is constant. What would happen if B had rates like A? Or could say, what should happen in population B if the rates from A applied? Now, all I'm going to do, guess what I'm going to do? The last time, when I wanted to say, let A look like B in terms of population profile, I transferred over the profile. Now, I'm going to say, let B look like A in terms of the rates. So I'm going to transfer the rates from A onto B. So now, here are the rates from B. I'm going to put 23.9, 0.7, 0.4, 2.5, 15.2, 69.3. So basically, I am saying, imagine what would it be like if the rates from A were to apply. So in the last time, what I did was standardize the engines. Everybody had the Mercedes engines. This time, I'm going to have different engines, but I'm going to standardize the gas. And say, what if everybody had the same gas? Let's see how the engines would perform, right? So this is B's engine. What would happen to B if it had rates like A? So now I can calculate the expected deaths in B if it had rates like A. So here goes. Number of deaths, same formula, will be equal to a death rate times population. So for the first category, the under ones, the death rate is 23.9 per 1,000. Notice, per 1,000 or per million or per whatever. A lot of times people forget the per. Multiplied by the population, 28,771. Remember, it says the standard provides the rates, the other population provides the numbers, the category profile. So if you do that, you should get, and let me hear for people who do it, let the rates from A, which we've superimposed, apply to B. Rates from A applying to B. What did you get for the first calculation?
687.6.
687.8, which we rounded up to 688. And this one, I'm going to allow you to do all of it because I want you to do a lot of work. So we're taking the rates from A and applying to B. and just make sure that you are getting those numbers.
68.7 for the second one, the 1 to 4.
68.7, correct. And we've rounded up that to 69. Good. I feel like I should commit a random act of murder. And so I'm going to see if I can murder Shalisa. What did you get for the third category?
Sir, I don't have my calculator with me.
You have your phone though, right?
Yes,
I
sir.
know you never leave your phone. So there's a calculator on your phone. You see? That's one person just been murdered. Let me see another one. Nashan, what did you get for the third category? The 5 to 17s. No Nashan? That means Nashan is dead. Second murder. Daniel, I know you're alive. What did you get? Wow, Daniel is also dead. What about Alex? Yes, Alex.
124.39, and I guess you're on it.
124.39, which we rounded to 124, correct? Alex, number 4 is yours, that 18 to 44.
I have a question, sir. I didn't
Yes,
get.
go ahead. Go ahead, man, go ahead.
I got 124,399.
Correct. That's because you didn't divide by 1,000.
Oh,
Mortality rate per 1,000.
1,000. Okay, got you.
I'm happy you made that mistake because you won't make that mistake ever again in exams. I see it many times in exams that people look at the mortality rate and they don't read the top. I see it's mortality rate per 1,000. So you have to divide by 1,000. Cheryl, what did you get for 18 to 44?
447.505.
447.5, perfect, which we've rounded to 448 on this example. So we are moving along quite nicely. And therefore, I know that Simone, you're not going to disrupt the flow. What did you get for the fifth category, 45 to 64?
Working on it, sir. Working on it.
I love that attitude.
All right, that's 1,808.587.
And so we rounded up that to 1809. Wonderful. And now, to take the cake with age category 65, I'm going to the bottom of my list and I see Wasemi, who is going to top it off nicely. What did you get, Wasemi?
Hi, sir. Just give me a quick second.
You are entitled to more than a quick second.
Wow.
You can even take a slow second. Wasting 1 second you asked for.
Okay, I got 2,831.7.
Excellent. And so you rounded up that, I rounded that up to 22832.
Yes.
Now, here is the next step. We've generated the expected debts that would occur if it had rates like A. And now we are going to do a slight variation. We're going to total the number of debts. So we total the number of debts. And if you do that, you will get 5969. Somewhere around that. So what it's saying is that if it had rates like A, if it had the force of mortality that is operating in A, if it had a grim reaper that looks like the one that's sweeping through A, we would have expected 5,969 deaths. Good. So somebody says, but how many deaths actually occurred in B? If it was just like A, we should have been seeing 5,000 deaths. How many deaths actually occurred in A? Anybody can tell me? Looking at the chart, not A, B. How many deaths actually occurred in B? If it looked like A, we'd have had 5,969. What was the actual number of deaths observed in B?
7,891.
7,891.
7,891. This is what was observed. Let me write a little better than that. So this is what was actually observed. 7,891. And we expected 5,969. Now, without doing any calculations, just let's think about what that means. If people are dropping out, totaling 7,000, when only 5,000 should have died, what does it tell us about B? 5,000 was expected, but we are actually seeing 7,000. What it tells us about B? B is more deadlier than expected, right? B is deadlier than expected. B is more deadly than expected. Because 5,000 would have been expected if it looked just like A, but what's happening B is 7,000 are dying. That immediately intuitively tells you what? That after adjustment, death rates in B are going to be higher. Intuitively. So what we do next is we compare the observed deaths in B to that expected if it really looked like A. If B had rates like A. So we compared observed deaths to expected deaths. 7,891 to 5,969, and we get 1.3. This ratio obtained by calculating the observed to the expected is called the SMR. The standardized mortality ratio. Now, immediately something's supposed to ring your bell, a bell, to say, when I had done it before and using the other method, it told me that the SMR should be 1.3. Suggesting that death rates in B after adjustment are 1.3 times higher. people are dropping off at a higher rate, 1.3 times more. So, notice we want to calculate adjusted rates. So what we are saying now is that if death rates in B are 1.3 times more, the force of mortality driving events in D is 1.3 times higher than what would be if it looked like A in terms of rates. Then the rate must be 1.3 times higher than A. What is the rate in A? 14.3. So 1.3 times higher means 1.3 multiplied by 14.3. Roughly 18.9. Now, I had done this in an Excel sheet, so it's got lots of accurate decimal places. But had you round it to 1.3 and multiply by 14.3, you'd have got roughly 18.5. So it says using the indirect method, the death rate after adjustment would be 18.9 per thousand. Using the direct method, the death rate was 17.9 per thousand. You notice that the methods give you a slightly different answer. They're in the ballpark, 17 is 18. But they are slightly different. And later on, we'll explain to you why they are slightly different. But in any case, the conclusion is that death rates are about 1.3 times higher after adjustment than in the standard population. So after controlling for age, using the indirect method, rates are 1.3 times higher. And the adjusted rate is 1.3 times the basic. You multiply by the standard because that's your yardstick. So if it's 1.3 times more than the standard, it must be 1.3 times 14.3, which is the standard. In this step, notice you had to generate the SMR first and then do a further calculation so that you could get the standardized death rate. Because you didn't get it directly at first, this method is called the indirect method. You get the SMR first, and then you generate the rates. In the first one, we generated the rate right away off the bat. We got it directly. The second one, we have to get the rate indirectly by this intermediate step. But notice why I said that nowadays people are saying CMR, SMR, it don't matter. It's still 1.3.
Right.
And more books are just talking about SMR. Standardized. You can know which method somewhere they will talk and say which method they used. So after adjusted for age, were it not for the age differences, we see that the risk of dying in B is 1.3 times higher than in A. So we have seen the direct method and we have seen the indirect method. For reinforcement, here's another chart. It has population A and another population B, and another population C. We have the profiles. We have the rate, the deaths in each population, the rates in each population. We have the same for B, deaths and rates, and we have the same for C, deaths and rates. We are looking at A and B. Those are data from 1996. Population C is from 1970.
Doctor?
Sure, go ahead.
Yes, sorry to cut you. Could you make it a little bit bigger for me, please? I'm using a computer, so it's quite small for me.
Oh, all right. Right. This is why we offer. All right. Let me see if I can go up a little bit.
Mm-hmm.
All right.
Thanks much. Appreciated.
All right. No problem. So here we have data, 3 sets of data. We could standardize, we could decide on a standard population. We can decide on what methods we want to use, and we can compare what we want to the standard. So we can standardize B based on A as the gold standard. We could standardize C based on A as the gold standard. We could actually standardize C relative to B if we decide B is the standard. We can do all kinds of things. We can compare populations at similar time. We can compare populations across different time periods, as long as we are engaged in the business of comparison. So we see from the data, all that, sorry, my fault. Come along. All right, let me just allow the screen to catch up. All right, we can see at the bottom of the table, the unadjusted rate. So overall, the death rate in population A is 7.63 per 1,000. The death rate in B is 4.87 per 1,000. And the death rate in C, crew death rate, no adjustment, is 3.72. So offhand, A looks like it has the highest death rate, B the second highest, and B has the lowest death rate. I mean, C has the lowest death rate. Just crudely looking at it. Paying no attention to confounders such as age. But a big question is, should we pay attention to age? Let us say that we want to compare population A and population B. Death rates, 7 points, crew death rates, 7.63 and 4.89. Based on the adjustment, it would appear that B is doing much better than A. But is this a question of age distribution? Is one population much older than the other? And therefore, do we need to adjust? We can do a quick check. We don't have to do it for all the categories. Just let's do some quick checks to see what the population distributions are like. Let's look at age 1 to 4. You could have done it for all of the categories and work it out, but I'm just going to choose age 1 to 4, and then I'll choose out of the top of my head age 55 to 64, just to see what's going on. You could have chosen age 1, you could have chosen 1 to 4. Proportions. In population age, A, the 1 to 4 group is 64,718 out of 1 million. And that should yield, I think that's 6.4%. Yes, 6.5% roughly. Everybody agree? 64718 divided by the total population of 1 million should give you 0.064718, and then 0.0647 is 6.47%, roughly 6.5%. And which other one I randomly had chosen? Oh, 55 to 64. 80,000 out of 1 million. So that's about 8.02%. 8%. Let's look at what's happening in B. Are the populations similarly distributed? You could have worked it out for all the categories, but I'm just going to use 2 just to make the point. 185,796 out of 1,048,222. This must be 13% or even higher. 18.5%. And the 55 to 64 group, 42,000 out of 42,083 out of 1,048,222.
2.1%.
4.2%. So if we compare it, you can see immediately that the age composition is different. 55 to 64s, the population is roughly, the percentage composition is roughly double that in A compared to B. You know, it's twice as high in A. And the other way, it's almost 3 times for the age 1 to 4. So B apparently is a much younger population with less older folks, and A appears to be a population that has less proportion of young people and maybe more older folks. This is just off the bat. But you could go and work out the entire population distribution if you want. But remember,
Prof.
earlier we said,
Excuse
ahead,
me, Prof.
someone. Yes.
Yes, I'm sorry. I lost power for a few minutes right after you said in the 1 to 4 population. Did I miss a lot?
All right. So which one did you see the 6.5% or did you see the 18.5?
No, I didn't see any of that.
Any of that. All right.
My power.
So what we did briefly was we worked out the percentage composition in A of the 1 to 4s. So it would be 64,000 out of 1 million. And that worked out to 6.5%. We also randomly just chosen some other categories, looked at the 55 to 64. And that would have been 80,294 out of 1 million, 8%. So in population A, 6.5% of the population is 1 to 4, 8% of the population is 55 to 64.
Okay.
We went over to B and we said, what is the composition of B like? For comparison, the same 1 to 4 population. 185,796 out of 1,048,222. And if you work that out, you'll get 18.5%. And similarly, we did it for the 55 to 64. We said in B, what proportion of the population is age 55 to 64? 42,083 out of the 1,048,222. And that worked out to be roughly 4.2%. So now we can compare. And we see that the underlying age distributions are very different. The proportions of people in the various age groups are different. And we know that that alone can drive death rates. So if we are going to be looking at whatever death rates and comparing it, we may need to adjust to account for the differences in the underlying distribution of the factor of age. So far, I'm doing age, but I could have done sex. I could have done income in terms of categories instead of under 1 and 1 to 4. I could have had under 20,000, 20 to 40,000, 40 to 60, and so on. Can do anything in terms of the categories. All right. So it means there are differences. If there are differences, perhaps we need to account and control for this because this can be a confounding factor. We have methods for controlling, one of which is standardization. So we could standardize these one population to the other and then compare. So I am going to say, let us, just because it's practice, let us use the direct method. And I have designated population A as the standard. You have to choose the population, or if it's a question, they may choose and tell you what the standard is. Once you know what the standard is, you decide on a method. Let's say we are going to use the direct method for practice. Now, in the direct method, if you go to your adjustment handout, in the direct method, the standard population provides the population numbers, the profile, and the other, the rates. So we are going to say, let the profile of B look just like A. Let A provide all the population numbers. So A has actually provided the population numbers here already. What we need to do is to have A provide the population numbers for B and to look, and for B now to look like A. So we're going to superimpose the population numbers. 15,343, 64, 718, 170, 355. Now, after a while, you get hang of it, and you could have just do the multiplication yourself, but just for teaching purposes, 162, 066, 139, 237, 117, 811, 80, 294, 48, 426, 17, 303, 2770. And of course, when you add those all up, it's going to come to 1 million. So now, with that, B looks just like A. A is providing all the population numbers. So we get rid of B's population numbers in theory. Let it look like A. Direct method, the standard provides the population numbers, the other provides the rates. So we are going to apply the other rates, the other being population B, to the population numbers from A. It looks now like A. So A is the standard, B is the other. So now we apply 32.992 multiplied by 15,343. And please remember, in this case, it is mortality rates per 1,000. So for the first category, we should be getting 32.992 per 1,000 multiplied by 15,343. And we want everybody to do that one and tell me what you get.
Five zero six
0.19.
506.19.
6.
And that's there on the sheet. Now, for ease, we are going to assign the remaining categories to some people so that we can browse through a little faster. And so, 1 to 4, that's Tanisha. Or no, not Tanisha, Tasha, Panton, 1 to 4. Vanessa, 5 to 9. Veronica, 10 to 14. Vonetta, is the next one is 10 to 14, 15 to 19. Stacy Ann, 20 to 24. Akeem, 25 to 29. Smart guy, who is very smart today, 30 to 34.
What are you looking at?
I think these 5-year categories is 5-year or 10-year. Let's see. I think there are 8 categories, something like that. Oh, some of them are 10 years, yes. So let me readjust. But if your name was called 4th, you are doing the 4th category. Your name called 5th. So that's 15 to 24, 25 to 34, 35 to 44. I think I would probably be somewhere around there. Alex, 45 to 54. Cheryl, 55 to 64. Kay, 65 to 74. And Nicole, 78 to 84. And Oshina, you'll do 85 plus. At the same time, others, if your name has been called, has not been called, you should be working through them. But I'm going to call on those people to provide me with the answers. All right, so let's get down to the nitty-gritty here. And if there's anybody who I've called and can't read the numbers, and you want me to read them for your category, let me know.
Okay, sir. So for Tasha Panton, age group 1 to 4, I got 90.216.
And you're on the money, which we rounded off to 90. So you won a prize like Digicel. And I tell you, the prize is the entry ticket to the big draw, which puts you at a 1 in a million chance of getting the prize. But you got the prize for buying credit. 5 to 14. Who's next?
Yes, sir. I got 102.38 and I round it off to 102 dates.
Correct. 15 to 24.
I think Veronica was before me, but I did that one. I got 232.7 to 233.
Beautiful. 25 to 34.
Maybe that was me.
Anybody?
Oh, I think that was me. I got 289.6 and it's rounded up to 290.
Great. 35 to 44.
That one is me. I got 499.443, running up to down to 499.
Correct. 45 to 54.
Oh, well.
I believe.
What Jenna do?
And you got what?
I think I did the wrong one because I did 55 to 64. And I got 15.
That's fine. You tell
26.
me what you got for 55 to 64.
1526.
All right, great. Anybody who did 45 to 54?
So I got 1005.9, which is 1006.
Great. 65 to 74.
Got 1,987.55, rounded up to 1,988.
And 74 to 84. Anyone who did it who has not yet answered can volunteer their answer.
I got 1614.5, which would be 1615.
Great. 85 plus.
55731. Leaving it to 557.
All right. So, with all that said, I have to engage and keep people awake. With all that said, now we go to the next step. These are the deaths which would have occurred in population B if it was just like A in terms of the age profile. Now, can we calculate the total deaths? Because we want an overall figure. Yes, we can. And if you add that all up, all those figures, you should get the total deaths being 8412. We can just confirm someone who has done it. And once somebody tells me they got that, I will move on. $506 plus 90 plus 102 plus 233 plus 290 plus 499 plus 1006 plus 1526 plus 1988 plus 1615 plus 557.
Yes, sir. That's what I got. 8412.
8412. Correct. So we've got the total deaths. Do we know the total population? Can he calculate an overall death rate for B? Now it looks like A. So it will be 8,412, which is the number of deaths total over the total population. And remember, the total population is now the figures that are here in purple. It's just like A. So the total population is going to be 1 million. So it's 8,412 divided by 1 million, which gives 8.41 per thousand. So the adjusted rate is 8.41, using A as the standard and using the direct method. Comparing, going a little step further, just to strengthen and to show off, you know, what they wanted was the age-adjusted rate, but just to show off that you really understand, you can say comparing the age-adjusted rate for B with that of the standard, and the standard is, of course, A, we would conclude that the risk is 1.1 times higher in B than the standard. How did I get the 1.1? Anybody has any idea? Well, we are going to compare the 8.41, which is the new rate, to the standard. The standard compares to itself is basically 7.63, doesn't change. So it's 8.41 divided by 7.63. Note that the rate for the standard always goes in the denominator, because you are comparing something to standard. It's 5 to 1, 5 to standard, 6 to standard, 105 to standard. So this time the adjusted rate 8.41 to the rate in the standard, which is 7.63. So the standard rate is always going to come in the denominator. And when you work that out, you get 1.1. So it tells us that the rate of death in B, having adjusted for age, is 1.1 times higher than in A. Right? Not for the age thing going on. Risk of dying in B is 1.1 times higher than A. Direct method, done. I'm going to use the same data and do the indirect method for practice. Same scenario, but indirect method. And what is our standard? The steps in standardization: choose a standard, choose a method. A will be the standard. So what we have to say is A is the standard, and we are going to use the indirect method. So the first thing you have to kind of know how the indirect method goes. In the direct method, the standard provides the age or population distribution, population numbers. Whether it's age, whether it's sex, whether it's income. Population numbers come from the standard. In the indirect method, what does the standard provide? The standard provides the rates, and the numbers come from the other population. So we'll get the numbers from this other population, which is B, the other than the standard, and the rates will come from A. So we are going to say, what would happen in B? Notice we're not saying what would happen in the standard, because the standard is fixed. What would happen in B if it had rates like the standard? So here goes, rates like the standard. So it means that we need to take the rates from A, the standard, and apply them, superimpose them into B. Let B have rates like A. So this becomes 29.32, is it 5? 329? 29.329. This becomes 1.545. This becomes 0.916. This becomes 0.826. This becomes 1.246. This becomes 2.205. This becomes 4.295. 16.714. 41.775. 99.347. And then 242. Let me write that to the side. So that they're hard. 242.960. That's the rate for the 85. So now that we've superimposed them, we can then do our procedure. How many deaths would occur in B if it had rates like A? So we're going to take the rates from A and multiply that by B. B's profile. So the rates from A are to apply to the numbers from B. So the first one, 29.329 rates, 29.329 per thousand by 23,703. So this is our expected deaths, our expected outcomes. And what did you get for that? Someone, 29.329 per thousand.
695.185.
695.
What did you get?
695.185. 287.
0.185, which we rounded up to 695. Good. And so I'm going to go silent for a while and allow you to work through that. And allow you to at least total the expected deaths. So the procedure is apply the rates, see what the deaths will be, then generate the expected deaths. Use the red ink instead. Oops, I'm sorry. I accidentally shifted. So just allow my screen to come back up. Go back down.
0.70.
Sure, the camera is on.
All right, yes, going back. So that just in case somebody doesn't have access to the data. Oh, medium move.
Ariel, we can see you.
It's okay, Cheryl. I know it's the camera that's misbehaving, not you, right? They sometimes develop a mind of their own.
Definitely so, sir.
See? You know what I love about you? You just confirm truths so easily, you know? All right. So let me go down, and then if anybody hasn't reached the end, you tell me where you reach and I'll wait for you. Did everybody get 287? Second category. Did everybody get 306?
Yes, sir.
Sir.
Did everybody get 121?
Yes, sir.
Yes,
Did everybody get 212?
Mm-hmm.
Yes, sir.
183?
Yes, sir.
126?
Yes, sir.
All right. And then I'll just allow a couple people are still finishing up. So let me stop there. And once they're on the right track, they should keep going. All right. Going into the next category. Did you get 703? 923?
Dr. James.
12 point. 12 point how much? 0.5. So we round up to 1013. And 203. So you generated the expected deaths that would occur if the rates from A were to prevail and apply to B. We are doing which method again? Indirect. Indirect. So the next step is to do what? In the indirect method. We need to total the expected deaths, and we also need to make note of the observed deaths. So let's total the expected deaths. $695 plus $287 plus $306 plus $121 plus $212 plus $183 plus $126 plus $703 plus $923 plus $1013 plus 203, and so the golden ball at the end is what? 4472, roughly. So now we have our total expected deaths. Our handout reminds us that in the indirect method rather, when we get the total expected deaths, we need to do what? Total events. We need to also obtain the observed deaths. Oh, my screen is semi-frozen. It's coming up. So the indirect method, having done the calculations, multiply, we get the total expected cases or events, and we are going to compare the observed to the expected. So we go back. And what is the observed figure? So we see observed deaths here, 5108 in total. So now we can compare our observed to expected, the O to the E. The O to the E. And this will generate the SMR. The SMR standardized mortality, in this case, because we are dealing with death ratio, SMR, equals O to E. And I hope that during the exams, when you come up and you say O to E, we do not hear in the exam O to D, as I've heard on one occasion. And we do that, 5108 divided 4472 gives us 1.07. And technically, you could have rounded that if you wanted to be roughly 1.1. So the conclusion here is that deaths, the risk of dying, are 1.07 times higher in B than in the standard. Because in B, we were seeing 5,108 deaths, when only 472 were expected to occur. So people are dying more than we would wish in B than if it looked like if it had looked just perfectly like A in terms of rates. So this suggests that something extra is going on in B when you're getting 7,000, when you're getting 5,000 when you expected 4,000. So obviously it means B is dropping off at a higher rate, more deaths. So after adjusting for age, it is 1.07. The rate would therefore be 1.07 times higher than in the standard. The standard is, of course, which population? A, in this case. So if the death rate would be 1.07 times higher, can we calculate the death rate? It's supposed to be 1.07 times higher than the standard. Do we know the rate in the standard? Yes. It is 7.628 or 7.63. Roughly. 7.63. So if it is 1.07 times higher than in the standard, then the rate must be 1.07 times 7.63, which gives us 8.16 per thousand. When we did the direct method, we got 8.4 per thousand. In this one, it would be 8.16 or roughly 8.2 per thousand. So our figures are not exactly the same, but they are comparable. And that should suggest to you that whichever method you use, you should get an answer that can stand up. So in life, nobody does the two methods. We are just training you so that depending on circumstance, you can apply whichever one. All right. Now, just out of interest before I do the next 5 minutes and close, suppose when you did this SMR, you got an SMR. Let me find a totally different color because I don't want anybody to think that this is an actual calculation. Suppose, hypothetical. Suppose you got an SMR, and when you did the SMR, you got 0.0 over E, and when you did it, you got 0.76. What would that mean? Point 0.76.
0.76 times lower.
All right, 0.76 times lower.
Or
Not
it-
quite,
I
but you're
think it
onto
would
the
be
right track.
that would be 24%
It's
lower.
24% lower, but it is 0.76 times what it is in the standard. So it's going to be, it means that the rate in the standard, remember this is O, and this is lower. So there are less deaths are observed than what would be expected. If this is to come out to a fraction less than 1, the denominator, the numerator has to be less than the denominator. So if this is a fraction, 0.76 or between 0 and 1, it means that the top observed deaths are less than expected. People are dying less than you expect, which means that things are good. The rates are lower. How much lower? Well, if you're going to say how much lower, then you have to apply the same thing that you did when you were talking about relative risk. It's really 24% lower. And let me draw a Venn diagram and show you what that actually means. Not a Venn diagram, a bar chart. 0.76 means 0.76 to 1. Just like when you calculate this, 1.07 really means 1.07 to 1, but nobody writes the 1. So 0.76 means 0.76 to 1. This is in B, and this is the standard, because the standard is always in the denominator. So if I draw a graph, and I call this 1, 0.25, 0.5, 0.75, there's a scale going up, and I call this B, the rate in the standard is 1. Standard. The rate in B, having adjusted, is 0.76 times that of the standard. So it's 0.76 times that of the standard. .76 times that of the standard means that this piece remaining is 0.24. Make sense? Because this part is 0.76 up to here. And this gap between the two, this gap is 0.24. Because you need 0.24 in order to make it up to 1. So it's 0.24 lower. So B would be 0.24 lower than the standard, 24% lower, or we say 0.76 times. People don't like 0.76 times that off. It's correct, but it's not intuitive. Well, let's see. Can a relative risk be negative? Can a ratio be negative? No, because it's going to be risk in one versus risk in the other. So you can have a number versus a number. So your SMR is not going to be negative. It will be fractional, but not negative. All right. So that's what it tells us. Now, both methods yield the same thing, same answer. So the big question is, now that you have learned both methods, why did I bother you? I bothered you so that you can do this homework. Let's do the reduction. There are 2 questions for your homework, and we will start with them next week. And please, 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 please do them. If you don't do them, you won't benefit from the experience next week. Using the data provided, that is sheet 7, that same sheet with population A, B, and C. The sheet is here. They've extracted it for you, population C and B. It says, using that sheet, calculate the age-adjusted or standardized age death rates by the direct method. So using sheet 7, I want you to calculate it by the direct method, and you fill through. And then we want you to do the same using the indirect method. And you'll realize I've been even a little kind, but when you get to it. So I want you to do that on your own or in a group or with your friend. That's fine, because we want you to learn. That's question 1. And then question 2 says, the chief medical officer, who is not yet a graduate of East Province, looked at the 2000 mortality data in table 3 and boasted, it is clear we are doing so much better than West Province. Just look at the death rates. What would you say to him about such a conclusion? With the data provided and using West Province, so I've told you which one to use as a standard. Calculate age-adjusted rates for East Province by an appropriate method. Not saying anymore. This exercise is also self-discovery. It's what's self-based, self-directed discovery and learning. And then, now that you've calculated, what remarks would you make to the chief officer in East Province? And the data is provided here on page 14. There's a table. West Province, populations, deaths, mortality rates per 1,000 in West, and then you get East Province, and you have some data. And when you undergo your self-discovery, self-directed discovery-based learning, we will start next week, having gone through these exercises, with one of the reasons or one of the criteria that guide the choice of method.
Doctor?
So the first exercise, question 1, is dedicated or is aimed at getting you to be proficient in both methods. And then question 2 just pushes you a little bit to examine and see what you could do, given that you can hang a dog as well as shoot it. You will decide what you want to do using West Province as the standard. The question online?
Oh, yes, Doctor. How can I access this document? Is it posted in
Yes, it's posted on the class website.
Okay, cool. Thank you.
Sir, are
It's the
there copies?
usual class website.
Are there copies in the classroom, sir?
Would you like there to be copies in the classroom?
Yes, sir.
You would.
You can do a few.
You think that I should come in tomorrow and do it?
Yes, I'm coming tomorrow.
You're coming tomorrow. I would ask a question. Are you graduating? Because tomorrow is the chaos day
Oh, yes, it's true.
in terms of transport. Yeah, but we will make it available. There are copies. There are some students here in the classroom, and they have the full copies. And it is true that you benefit a lot when you have printed this material. It's hard to work on it just visually on the screen. If you can download it and print it, good for you, or you can pick up the printed copy. But I'm not sure if tomorrow is your best day for coming on the campus.
Okay, no problem.
Unless you really have something to do on the campus, it's not a good day. Because you will be caught in traffic from Mona Road to whenever. Because tomorrow, remember, is two graduations and one on Sunday, something like that. And tomorrow is the big one, which is social science, right? That has the thousands and thousands. Right, one in Saturday. I think one in Saturday morning, and it's social science Saturday morning. Tomorrow is what? Arts and
Yes, Saturday morning is social sciences.
Yes, and then tomorrow is what? Arts and general, what is the name? Arts and general studies and engineering. No, medicine, natural science, and engineering usually go. What am I missing tomorrow? Arts, and there's one other faculty somewhere. UTC.
Okay, no problem. Thank you. Looking forward to it.
But it's a double graduation, I think, tomorrow. All right. Thank you so much. You did quite well because this is not very easy online, but I think most of you follow the gist and the logic, and it's really practice that brings it home to you.
One last thing, sir. After we do the SMR.
Yes, after you did the SMR, you're using the indirect method. The SMR tells you how much higher or how much lower. So we need to calculate the actual rate. The SMR is the ratio. So when you get 1.3, it means it's 1.3 higher than the standard. Whatever figure you get, it means it is that multiplied by the standard. So you're going to get 1.3 or 1.07 rather in this case, multiplied by the whatever the standard was. The standard was what? 7.63. Yeah. And then you'll get the real rate, because this is very really saying that it's 1.3 higher than the rate in the standard. So if the rate in the standard is 7.63, then the actual adjusted rate must be 1.07 times 7.63. And it's indirect, so you have to go the extra step. So SMR and CMR, no difference. And in fact, some people are saying we must drop CMR and get it out of the books. But I actually saw an article recently with somebody who indicated CMR. What I used to say first time is CMR if you use the direct method, SMR if you use the indirect. But that has gone out the window because SMR and CMR give the same thing. You know, there's slight differences, 1.1 versus 1.07, 1.3 versus 1.32. You know, so people are saying that we just use one word. It's a standardized mortality ratio, which is actually because it's a ratio generated by standardized rates.
So we have 3 lectures, and we do have 4 to I give the course assignments that we have. We design a safety unfair because we have started how we do that.
Okay. I'm not sure if she has done the group assignments and stuff yet.
I think
But-
I'm here.
Eh?
I need to come here and know with me too.
I know you're always ahead.